Welcome back. In my previous video, I have seen what is the limit and continuity on multivariable function. Today, I will discuss this concept elaborately. At first, today I will see the geometry of function of several variables. Why here the points are vector? What is the geometry of function in multivariable calculus, level curve, and how in multivariable calculus the limit continuity, this definition actually geometrically used epsilon delta definition, other definition. At first I will say in multivariable calculus why here the point are actually vector. We all of us know this is because in the part of several variable I have first defined when the point in R2, R3, then always the point, not point. This is actually the vector. But today at first I will just as a review, today at first I will discuss this part. Then I will define again limit continuity in better way. Also I will define some theorem based on this property. This is actually today's goal of this lecture. Let's say our first goal. If we consider this geometry, this is the x-axis and this is y-axis and this is the point 0, 0. Then any point P which is represented as xy. Here any point xy is actually represent direction. That means this, if we consider this O, then this is OP and P equal to here vector which represent the direction, because we all of us know vector means it has a magnitude and it has a direction which has the direction OP and the point is, the P point is x comma y. That means here the point xy represent the vector OP where OP equal to xy. Point is vector because it has a direction and magnitude. If we consider other point in R2, consider this point is x dash y dash, then this point would be such type, here OQ. That means if we consider in R2 this type of circle, therefore we can choose this point, here all the point in this circle x square plus y square equal to 1 always be vector, and the space in R2 actually look like such type xy where x belongs to real line and y belongs to real line. Here all point in this space is vector. This is I have defined in my previous video when I had started the functional several variable. If you don't see my functional several variable, at first see my previous video. Actually today's video I have defined this part just as a review. If you see this part again, then you will define, you will in better way understand what is the definition, how here the actual meaning of continuity limit in the functional several variable. When the metric space is in R2, in R3, that means in Euclidean space, then how look like the geometry of graph, how look like the level curve. Okay, so I have defined this part actually. If we consider R3, then the point is look like such type x, y, z. This represent height, length and breadth. Okay, and in R3 the point is look like such type x, y, z such that x, y, z belongs to R. This point is vector because it has a magnitude and direction. This is the P point, and this similarly we can choose Q point, R point in R3 space. This is the R3 space, and R4 is the higher dimension. R4 would be such type, similar type of R3 x, y, z and T. T means here the temperature, where x, y, z belongs, T belongs to R. This point is vector because it has a magnitude and direction. This is the P point, and this similarly we can choose Q point, R point in R3 space. This is the R3 space, and R4 is the higher dimension. R4 would be such type, similar type of R3 x, y, z and T. T means here the temperature, where x, y, z belongs, T belongs to R. And we all of us know actually metric space, vector space all depend on higher dimension. In Rn the vector R, here the point, here x1, x2 up to xn, where x, y, z, x1, x2 belongs to R. Here actually the vectors, and Rn is actually called vector space of dimension n. This is actually geometry. How look like the point here, the vector, we all of us know. And in metric space, Rn is actually called Euclidean metric. I hope my all viewers have understood the geometry. We all of us know what is the vector space, Euclidean metric. But if you know the geometry, how look like the point, then you will understand what is the definition of metrics, what is the definition of continuity, differentiability in higher dimension. And if we want to find distance of P from the point O, and we all of us know this is actually, we have to find the length of OP, and this is actually length of OP means norm of OP, and this is actually square root of x square plus y square plus z square. I will say different type of function because if you know the idea of function in better way, then you will understand the definition, actually the geometrically. I have defined this type of function in my previous video. Today's video actually just as a review. If you understand in better way, this actually what is the function in several variable, how look like the graph, then we can define continuity limit in better way. First function, consider a function phi which is defined from R to R. Obviously the function would be such type y equal to phi x. Then graph of the function would be such type xy belongs to R2 such that y equal to phi x. Similarly, if we consider from R2 to R, then graph of this function would be xy belongs to R2 cross R such that y equal to phi, here z, here because R2 to R, z equal to phi of xy. Obviously this is this xy be the vector, As for example, if we consider z equal to x square plus y square, this is actually they look like the paraboloid. This is x axis, this is y axis, and this is z axis. We all of us know graph would be such type. When the value is 0, 0, then the value is 0, 0, and in other point the value is non-zero. Similarly, we can consider z equal to x square minus y square. This graph would be different type. This type of graph actually very important. If you know this type of graph, then you will understand why I have defined in the definition of limit. Why? The point goes to and another point mean here actually the vector, and here goes to means not only this line, here goes to means we can define infinitely many paths along this curve. So if you know the graph, then you will understand in better way. If we consider the function from Rn cross R, means here the graph of the function is of those x comma y belongs to Rn cross Rn R such that y equal to fx, where fx equal to f of x1 comma x2 up to xn. Here obviously this x1 x2 xn be the vector. Now if we consider the function f from Rn to R, obviously this type of function is actually linear function. We all of us know. And the graph would be here, the function would be such type. Consider a vector c belongs to Rn, where the vector c equal to c1, c2, cn. Then define fx equal to f of x1 comma x2 up to xn, which is equal to c1 x1 plus c2 x2 up to cn xn. Obviously this type of function is linear function, and we all of us know when a function be linear, a mapping f from Rn to R is linear if f of x plus y equal to f of x plus f of y for any xy belongs to Rn. Second, for any alpha belongs to R, f of alpha x equal to alpha times fx. If these two conditions hold, then we can tell our given function f, which is defined from Rn to R, is linear. We all of us know this is. And actually, linear function is defined in such way. Here this c1, c2, cn be the vector. As for example, if we consider one variable, that means f from R to R, then the function would be f of x equal to c1x. Then this is actually the line which is passing through origin. But if we consider f from R2 cross R2 to R, such that f of x1 comma x2 equal to c1 x1 plus c2 x2, this is actually the plane passing through origin. Now if we consider function from Rn to Rm, obviously this is be the matrix A of m cross n, where each row of A be the here vector, and here the function is defined as A from Rn to Rm, which is vector function, and which is defined as Ax, which is equal to r1 dot x, r2 dot x up to rm dot x, and this is equal to a11 x1 plus a1n xn, and here in this row am1 x1 plus amn xn. Obviously here the function is defined in this way, and this is actually the vector valued function, we all of us know. Now my question, if we consider this type of graph, w equal to f of x comma y comma z equal to x square plus y square plus z square. Now my question, can you visualize the graph? Obviously graph is in 4th dimension. We cannot visualize this graph. Here the idea is level curve. When we cannot visualize the graph, then the idea is level curve. We all of us know actually the level curve. Just as a review, for this given circle, here the level curve is x square plus y square plus z square equal to alpha, where alpha belongs to R, and this is actually the sphere center 0 0 0 with radius square root of alpha. We all of us know this is. Similarly, if we consider this type of function fxy equal to y square minus x square, then the level curve would be y square minus x square equal to c, where c is constant. For different value of c, I will get different type of function. When c equal to 0, then the line y equal to plus minus x. When c equal to 1, then the line graph is y square minus x square equal to 1. Since c equal to 0, y equal to plus minus x, that means this is for c equal to 0. For c equal to 1, the hyperbola y square minus x square equal to 1. This is the hyperbola for c equal to 1. For c equal to minus 1, here the hyperbola is y square minus x square equal to minus 1. This is. Similarly, I will get for c equal to 2, c equal to minus 2. This type of level curve, the picture of level curve would be such type. If you want to understand level curve in a better way, then see the playlist of my functional several variable lecture. I have defined different type of level curve in functional several variable chapter. Okay. Now I will see our actual goal of this lecture. In my previous video, I have seen in metric space what is the definition of continuity. I had seen f is continuous at a point A if for every epsilon greater than 0 there exists delta greater than 0 such that distance between x and A less than delta imply distance between fx and the limit point L is less than epsilon. This distance function we can define by norm. Consider a function f, here the open interval u who is subset of Rn to Rm, and consider a point x0 belongs to u. F is continuous at the point x0 if for given epsilon greater than 0 there exists delta greater than 0 such that if y belongs to in this open interval u, norm of x0 minus y less than delta. Here norm means consider this distance x0 and this distance y, and this length is norm of x0 minus y. Actually here since distance, so we can use this notation norm, that imply obviously since f is continuous at the point x0, that imply norm of fx0 minus fy less than epsilon. I hope my all viewers have understood why we have used here norm notation. These two definition actually equivalent condition, and we all of us know other definition of continuity is sequential criteria. Sequential criteria is in multivariable calculus. Consider a sequence xn which contain the set u and x0 be point in the set u. Here u be the subset of Rn, where the function defined from u which is subset of Rn to Rm. Consider xn converges to x0. Then by sequential criteria we can tell if f is continuous, then fxn always converges to fx0, and xn converges to x0 means when the vector valued function, this means actually norm of xn minus x naught tends to 0 because here xn converges to x naught, and this means actually ball around the point x naught of radius delta, ball means here ball x naught of radius delta, in this ball xn lies eventually. Now I will see one example. Function is defined from R2 to R and the function is such type f of xy equal to 2xy over x square plus y square, and this is defined when xy not equal to 0 0 and 0 when xy equal to 0. Is this function is continuous? If you fix x naught, then x naught yn always converges to x naught y naught. That means f is continuous in y. Similarly, if we fix y naught, then similarly f is continuous in x. That means f is continuous at every xy not equal to 0 0. Now my question, is f is continuous at the point when xy equal to 0 0? For this, consider the path y equal to x. Then f of x is equal to 2x square over x square plus x square, and this value is 2. But when the value of xy equal to 0, then the value of the function is 0. So f is not continuous when xy equal to 0 0. Okay? Sequentially, this definition would be such type. Consider a sequence xn yn such that xn equal to yn. Then f of xn yn would be 2xn square over xn square plus xn square, and this value would be 2, but f of 0 0 equal to 0 0. That means f of xn yn does not converges to f of 0 0. So this function is continuous when xy not equal to 0 0, but does not continuous when xy equal to 0 0. Then there exists one easy way to check continuity in functional variable. If f defined from U to R, which be the subset of Rn to Rm, and x belongs to U, here x belongs to U mean the component of x is n component, means x1, x2, xn. f of x1, x2, xn equal to, here this image would be m component, so f1, x1, x2, xn up to fm x1, x2, xn, where each fi map from U to R, where I equal to 1 to up to m. Then f is continuous if and only if each fi is continuous. That means if each fi is continuous, then we can tell the function f is continuous, and this proof actually very easy type proof. And in functional several variable, to check continuity, this process is easy process. This proof is very easy type proof. F is continuous, then always f is continuous mean each fi is continuous where I equal to 1 to m. That means here we have to show each fi is continuous when given f is continuous. That means we have to show given epsilon greater than 0, there exists delta greater than 0 such that norm of x minus y less than delta where xy belongs to U. That imply absolute value of fi x minus fi y less than epsilon. And norm of fx minus fy means actually square root of f1x whole square minus f1y whole square plus this would be continue here fmx whole square minus fmy whole square. Since the function is continuous, that means this value is less than epsilon. Therefore, that imply epsilon square less than f1 x minus f1y whole square up to fmx minus fmy whole square. Okay? And from this relation, we can tell since sum of the square less than epsilon square, that means each fix minus fiy, obviously each fi less than epsilon square for all I equal to 1, 2 up to m. Conversely, consider each fi is continuous. That implies always f is continuous because given epsilon greater than 0, there exists delta I greater than 0 such that norm of x minus y less than delta I imply absolute value of fix minus fyy. Consider this is less than epsilon over square root of m. I have considered epsilon over square root of m because minutes later you will understand this is in better way. Here I equal to 1 to m, and this relation is true because given each fi is continuous, and for each fi I will get different delta y. So consider delta equal to minimum of delta 1, delta 2, delta m. Then norm of x minus y less than delta, which is less than equal to delta I, where I equal to 1 to m. Then absolute value of fix minus fiy, this value would be epsilon over square root of m. This is true for all I. Then norm of fx minus fy, which is equal to square root of f1x minus f1y whole square up to fmx minus fmy whole square, and these since this each value is epsilon over square root of m, here since here square, so this value is epsilon over m times m, and this is less than epsilon. Okay, therefore that imply f is continuous. From this relation we can tell f is continuous. Therefore if each fi is continuous, then that imply f is continuous. This is another way to find in functional variable is one function be continuous or not. Here I will stop here. In my next video I will discuss this topic also, because this type of topic actually very important for any competitive exam and higher study. Okay, see you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.